Good afternoon, everyone. Today we are going to discuss machine learning from a security perspective. We will talk about attacks against machine learning, mitigations for those attacks, and we will review some examples of attacks that have occurred in the wild, as well as provide some high-level guidance on defending against these attacks. Before we begin, let me introduce myself. My name is Tim Sotack. I'm a senior AppSec consultant at Optiv. I've been with Optiv for about 1.5 years now. Previous to my work with Optiv, I spent many years working on secure development lifecycles with an emphasis on SAS, DAST, and secure coding.
Hello, my name is Nikhil, Ollukaren, and I'm a senior application security consultant, and I've been here at Optiv for 8 years. Here, I have worked with a number of Fortune 500 companies, helping secure their digital space from assisting in the design phase with threat modeling and SDLC support, all the way through to pen testing their deployed web, API, and mobile applications. I've had some past experience developing code, and new technologies like machine learning and artificial intelligence are very intriguing.
So to begin, we will discuss what is machine learning. I think everyone has some idea of what machine learning is, but I think it's always a good idea to have a working definition to go by. Here are 2 quotes I found that I think are useful in framing the topic. First one is from Arthur Samuel. It says that the field of study that gives computers the ability to learn without being explicitly programmed. Second one, which is more technical, is a computer program is said to learn from experience E with respect to some task T and some performance measure P if its performance on T as measured by P improves experience E. Now that we have a good working definition of machine learning, let's talk about the various ways that learning is done. The first way is supervised learning, and in this case, there exists a set of data that has some sort of label attached to it. It can be further broken down into regression and classification. For regression, the label that is used is simply the value of the dependent variable used in the regression. In the classification, the label is the class that the item belongs to. The second type is unsupervised learning, and in this case the data is unlabeled, and the data are classified based on proximity to each other in feature space. So some examples of this are clustering, anomaly detection, where you try to determine outliers, things that are out of place or don't fit in the normal pattern, and dimension reductions, which is essentially techniques used to reduce the dimension of the feature space, which will help with the performance of the model. The third category is reinforcement learning, and this is learning based on rewards. It's good for game-playing AI. In addition to those 3 categories, there's also another dimension, which is the time over which the training is done. And batch learning is done when it's confined to a specific interval of time. No additional learning is done after the initial training, and as the model grows stale or starts losing its accuracy, it will have to be retrained. In contrast, online learning is when the model actually learns as it goes. So this allows it to learn from the user input, which also makes it more susceptible to malicious inputs. It will be useful to review the high-level process involved in machine learning to better understand the security issues that may arise during the process. Given a problem, the data is gathered that is relevant for solving the problem. Based on the data and the problem that needs to be solved, an algorithm will be chosen. So the size of the data set, the type of the data, is it images, is it text, is it audio, and whether or not it's labeled or unlabeled will all help determine which algorithm to use. The chosen model will then be trained on the data. The model is then tested, and if the model is sufficiently accurate, then it will be deployed. There are multiple algorithms that implement the different types of learning we just discussed. Each of these has its strengths and weaknesses as well as domains of applicability. Recently, though, most attention has been on deep neural networks. The basic structure of a neural network is a graph of connected nodes or neurons organized into layers. Each neuron sums the inputs from each connection and applies an activation function to the sum to produce the node's output. Each connection has a weight, that is a variable that is multiplied by the output of the previous layer to produce the inputs to the next layer. The optimal value of these weights required to produce the desired output is obtained during training. Training is done by minimizing a loss function that measures the distance between the current output and the correct answer. Most neural networks being used today are deep neural networks. And these are neural networks with many layers. They typically require lots of data and are expensive to train computationally. They've been around quite a while, but have only recently come into their own, given the recent significant increases in the availability of data to train on and in the processing power that allows the training to be done in a reasonable amount of time. There are several different types of neural networks, including convolutional neural networks, recursive neural networks, generative adversarial networks, and large language models. Convolutional neural networks are used primarily in image processing applications, and they implement what are called convolutional layers that do some additional processing that allows learning to be done more efficiently. Recursive neural networks feedback outputs from neurons back into themselves, which is then used to produce new outputs. They are typically used for anything that involves sequences, which includes text processing and time series prediction. So you may run into LSTM, GRU, or bidirectional. These are all different types of recursive neural networks. Generative adversarial networks involve connecting two networks together so that one can essentially train the other. An example is teaching one network to generate numbers by feeding data back from a network that is trained to recognize those numbers. So based on the feedback from the one network, it'll keep improving until it produces something that is acceptable to the other network. And finally, large language models. These are trained on very large sets of text data and produce human quality sentences in response to prompts from the users. Of course, these include ChatGPT and Hugging Face GPT as well. Now that we've given a brief overview of machine learning, let's move on to discussing attacks on machine learning. For the purposes of this talk, we will be focusing on machine learning specific attacks. Standard attacks against the infrastructure and software components used in the machine learning process are also quite important, but they will not be the main focus of this discussion. A recent NIST publication on adversarial machine learning reviewed the recent literature on ML-specific attacks and concluded that most attacks occur during the training stage or the deployment stage. So the training time attacks, they occur during training, and they attempt to change the behavior of the model by modifying the training data or the labels during the training process. Deployment time attacks occur once the model is deployed. They're also referred to as inference attacks. Before discussing attacks, we should review the different capabilities that attackers may possess. Controlling the training data is one such capability. In this case, the most powerful attacker can control both the data and the labels for that data. More limited is being able to only control one or the other. Label flipping occurs when the attacker can control the labels. Clean label attacks occur when the labels cannot be controlled, but the data can be controlled. And this is considered the most realistic attack capability, since in many cases the attacker may be able to provide data to the training process, but may not be able to control labeling, which may be done in a separate process altogether from data ingestion. The next capability is controlling the model. In this case, they may be able to change it in ways that produce their desired outcomes. And finally, the most limited capability is query access, where the attacker can only make queries to the model and get results back from that query. Machine learning attacks can be grouped into three categories: evasion attacks, poisoning attacks, and privacy attacks. Evasion attacks are deployment time attacks that attempt to induce misclassification of a sample. When the model is presented with a so-called adversarial example, the model will misclassify the item. In poisoning attacks, the data used for training is tampered with to produce various results desired by the attacker. And privacy attacks are attempts to extract information about the training set used to create a model or about the model architecture and its parameters. So first we'll talk about evasion attacks. So these are done at inference time. A malicious input is used to produce an incorrect output. The goal is to produce misclassification using an adversarial example. These attacks can be classified into white box attacks and black box attacks based on how the adversarial example is produced. In white box attacks, the attacker has access to the model and can query the model to produce the example. Many of the ways to produce the examples use optimization-based methods that produce a perturbed input that is likely to be misclassified. These methods all attempt to find the minimum size of the perturbation to the input that will induce misclassification. The simplest method is called the fast gradient sign method, and it simply takes the gradient of the loss function, which is available from the model, and adds a multiple of it to the original input. Projected gradient descent and Carlini-Wagner are more sophisticated methods for generating the examples. We will focus on FGSM since it is the easiest to explain but gives the general flavor of these types of attacks. Here's one of the classic examples of the fast gradient sign method. Here the input image clearly is a panda, and it's correctly classified as a panda by the original model with a 57.7% degree of confidence. To that original image, we add a small multiplicative factor of 0.007 times a perturbation, which looks a lot like noise. When that perturbation is added to the original image, we get what to the human eye still looks like a panda, but is misidentified by the model as a gibbon. And not only is it misidentified, it's misidentified with a high degree of confidence. So what's interesting about this is it indicates that whatever the machine is doing to identify the image is considerably different from what a human's doing, because a human can still tell that that's a panda. As a matter of fact, it looks very similar to the original image, and it's hard to tell the difference. Here's another example, which is more concerning than the previous example of misidentifying pandas. In this case, a physical stop sign was modified in such a way to induce misclassification by the types of systems that may be used in self-driving vehicles. So clearly this has significant implications if you can induce a self-driving vehicle to ignore a stop sign. You'll notice that the perturbations are obvious in this case as opposed to the other case. So a human can easily spot that it's been perturbed. The significant question is whether or not that perturbation would be enough to induce the replacement of the stop sign by the authorities. The second category of evasion attacks is black box attacks. All the evasion attacks discussed thus far have required access to the model itself to generate the malicious inputs. Black box attacks do not require such access. The attackers in this case do not have access to the model parameters, but only to the model output. These can be grouped into score-based attacks and decision-based attacks. In score-based attacks, the attacker can access the model's confidence score, which may be included in the output. In many cases, however, the confidence scores may not be included in the output, and the attacker has access to the classification results only, in which case decision-based attacks need to be used. Principal challenge in doing these attacks is it generally requires a large number of queries to perform. It is important to note a feature of evasion attacks called transferability, which makes it possible to use white box attacks against a system where only black box access is available. In machine learning, transfer learning refers to using a pre-existing model and tuning it for your particular needs. For example, if you have a small set of images of food that are not adequate in and of themselves to train a deep neural network, you can reuse a model trained on a large data set of images that's not necessarily limited to food and tune it to only classify food items. The idea is that the lower levels of the model capture more low-level features of images in general and may be reused for any type of image. So the process involves stripping off the top layers of the model, adding some additional layers that will be trained to recognize the food, and then retraining those top layer models, and then tuning it so that it correctly identifies the food. The security implications of this is that if someone uses a model similar to or based on a model that is openly available, then an attacker may use white box techniques on the available model to produce malicious inputs that may transfer to the derived model and induce misclassification on that model. So how can evasion attacks be mitigated? Three methods that have been proposed are adversarial training, randomized smoothing, and formal methods. Formal methods are the least practical, and so we will focus on the other two. Adversarial training involves producing adversarial examples using one of the methods we discussed earlier, and using these examples as part of the training process. They will be included in the training data with their correct labels so that the model will learn those in their proper classifications. So if they see these adversarial examples in the real world after deployment, they will be able to properly identify them. Randomized smoothing is similar in that it produces perturbations to training samples to make the decision boundaries more robust so that small perturbations will not cross over decision boundaries into another category. There are trade-offs between the accuracy and robustness for all of these techniques, as well as the additional effort required to include them in the training, as well as an increase in the training time. The next class of attacks are poisoning attacks. Poisoning attacks are training time attacks against the training data or the model itself. There are several variants of poisoning attacks worth mentioning. First is an availability attack, which is intended to induce an effective denial of service against the model by degrading the performance of the model to the point where it's useless. The second is targeted poisoning attacks, which insert a small amount of incorrectly labeled data to the training set. The third is backdoor poisoning attacks, which attempt to associate a trigger with a desired label, such that misclassifications can be induced in any of the inputs by adding the trigger to the input. And finally, model poisoning, where the model itself is changed to induce misbehavior. Typically, the model poisoning attacks occur in federated learning environments, where there's separate nodes, each doing their own processing, and they all contribute updates to the main model. Backdoor attacks are one of the more popular type of poisoning attacks due to their utility. One of the more interesting examples was a physical backdoor attack, which induced misclassification of people in facial recognition systems based on physical triggers. Listed here are some of the triggers that are used. It includes dot stickers, sunglasses, temporary face tattoos, white tape, bandanas, and earrings. The author noted that earrings were the least effective, and the most effective were the modifications that altered the region of the face around the eyes. So how do we mitigate against poisoning attacks? In general, locking down the training data and models will help to mitigate these attacks. If you're using third-party data or third-party models, then you have to be particularly careful about the origin of the data and the origin of the models, and also about the integrity of it. So data set origin and integrity attestation would be very important to help ensure that the data being used and the model being used has not been tampered with and comes from a trustworthy source. For backdoor poisoning, efforts have been made to help identify backdoor data so that it may be removed from the training set before training is done. The identification of the backdoor data is often done by identifying outliers in the training data. Another approach is to reconstruct likely triggers for the model so that they can identify any inputs that have been backdoored and remove that data from the training set. The final approach has been to develop tools that inspect the model itself to help determine if there's any backdoors in the model. And this includes a meta classifier that predicts if a model is backdoored. And this is essentially a machine learning model that is trained to detect backdoored models. For model poisoning, it seems a little difficult to defend against. The quote from the NIST publication basically states, designing federated learning models that are fully robust against model poisoning attacks remains an open research problem in the community. So it seems that once a machine learning node has been compromised, it's difficult to prevent the model from being poisoned. So the best defense here seems to be to lock down any nodes that participate in model updates in a federated learning system to make sure that they can't be compromised. The final type of attack against machine learning are privacy attacks, and these involve disclosing sensitive information that may have been used in producing the model. These attacks are generally based on query access and require a large number of queries to be effective. They can be classified into several different types. The first type is a data reconstruction attack. This attack attempts to recover individual training samples from aggregate statistical information. The second type is memorization, which occurs in generative models and refers to the phenomena of the model memorizing specific information about training data that can be recovered later. The third type is membership inference attacks, and these attacks to determine if a given individual was a member of the training set. So dependent upon the nature of the model, being a member of a particular training set can potentially disclose sensitive information about a given individual. The fourth type is model extraction, and this attempts to reconstruct the model based on responses to queries. If you can reconstruct the model, you could create other types of attacks like evasion attacks by querying that reconstructed model. The fifth type is property inference attacks, and these are used to infer global properties of the training set. So how are privacy attacks mitigated? The most promising approaches thus far are those that implement differential privacy during the model training. Differential privacy is defined as a system for publicly sharing information about a dataset by describing the patterns of groups within the dataset while withholding information about individuals in the dataset. The gist is that several algorithms have been developed to train models with differential privacy, and that these algorithms can be used to mitigate against privacy attacks that we just discussed. There are other approaches to mitigation that includes limiting queries to the model in attempts to detect suspicious queries, but these are not generally considered as robust as training with differential privacy. And differential privacy, of course, has trade-offs associated with it, including model accuracy and performance of the model.
Now let's take a look at some real-world examples of these types of attacks to help better understand the way that threat actors have exploited, deployed machine learning applications. While this is not meant to be an exhaustive list of exploits, we wanted to highlight a few that stood out to us and tied closely to the different attack methods described earlier. These 7 examples range from covering basic supply chain attacks to black box ML exploitation. We will also see how, with the advent of several emerging technologies, all focused around scaling machine learning models, how much easier these attacks have become to replicate cost-effectively. Let's dive in. When talking about new technologies, we can sometimes only view the unique parts when considering machine learning. Sometimes the simple, tried and true methods are good enough to exploit the machine learning field. There are a number of open source repos that are leveraged in developing machine learning applications, and one of them is PyTorch. In 2022, from December 25th, to December 30th, there was a rogue package that would be installed via pip if the developer had nightly builds enabled for their application. An attacker was able to do this due to the fact that a dependency did not exist on the pip, which is the first location pip looks for the build packages, but it did exist on PyTorch's index. Whenever a build would run, pip would check in with pippy first and then go to PyTorch index. The attacker was able to register a package using the same name called Torch Triton in PyP, and pip used that one since it now existed in the primary index. This led to the exfiltration of sensitive data from the victim's machines and is a classic dependency confusion supply chain attack. Now, let us take a look at leveraging deep learning as the attack payload itself. Lots of mobile applications now use deep learning models to better present content to their users, and these neural nets are logic black boxes. However, attackers have discovered ways in which they can inject their own deep learning algorithms as payloads into the mobile application. This attack is a type of poisoning attack, and the payload is able to use conditional branching logic with a triggered detector and several operators to navigate the victim's model. The researchers were able to take 5 popular deep learning models and real-world samples collected from 30 users and inject the payload with a success rate of 93.5%, where the backdoor successfully triggered in the app. They also used their payload on a number of applications on the Google Play Store, further illustrating the capabilities of this type of attack. This attack would need to be chained with a supply chain compromise similar to the previous PyTorch vulnerability we saw, since the injected APK would need to be reloaded into the victim's device. In this real-world example, we have a popularly used anti-malware tool, Kaspersky. Kaspersky's anti-malware detectors were discovered to be vulnerable to especially crafted evasion attacks. The evasion attack was a transfer-based attack where an adversarial sample was created from a proxy model and was successfully deployed to the original model. This worked on the anti-malware by performing feature extraction on the local machine and sending the features to a cloud-based detector, which would then return the classification of the scanned objects. The attacker proceeded to gather a sizable set of malicious and clean files and ran them through the detector, producing a large data set of labels for each file. The attackers were then able to create a proxy model based on the labeled data sets for the files and started generating adversarial examples. These used the information on what features had passed labeling and were successfully used against the original model to bypass the malware detection. We are also seeing machine learning deployed to identify individuals based on their facial features. In this exploit, attackers are using publicly available data about an ML model and compromised or valid accounts with access to the ML's API. With this ML model inference through API access, the team identified the list of identities targeted by the model by querying the AI. The team then used open source data sets and trained their own proxy model to begin crafting adversarial visual patterns. These optimized adversarial visual patterns were physically deployed patch-based attacks that leverage expectation over transformation. Expectation over transformation is the way an ML model figures out how an object should look in varying environment factors, such as orientation, distance, lighting, etc. The attackers were able to then add these patches to the environment to impact the facial recognition. This technique has been leveraged by exploits such as Shapeshifter, which is a robust physical adversarial attack on faster RCNN object detector and can impact recognition of signage, like stop signs, which can be deployed against autonomous driving systems. With regards to facial recognition, it should be noted that there are currently some anomalies with the eyes when creating artificial renditions. There are also ways that you can create a statistical model for the way faces transform when they move to check if the values are faked. One of the common threads that we see in these exploits is that threat actors turn first to publicly available information about the ML to begin crafting their exploits along with any compromised access to the APIs. While it is a common reaction to want to black box most of the information, we have seen that that's not always an effective deterrent. As we have open source code that promotes transparency and vetted security by the community, ML models will begin to have more implementable safeguards and input checks along with secure design practices. In this example, the Azure Red Team used publicly available information about the ML model and crafted an automated system that continuously manipulated the original target image by making subtle modifications to the image unnoticeable to the human eye. This attack is a poisoning attack, and the inputs began to shift the ML model's ability to classify the targeted content. This example is focused around learning ML exception cases and leveraging them against the model. The attackers were able to carefully analyze the malware engine and ML model of CYLANCE'S AI-based antivirus product and identify a particular bias. In this case, there was a specific game whose contents had a special categorization in the ML weighting. Combining an analysis of the feature extraction process, its heavy reliance on strings, and its strong bias for this specific game, the threat actors were able to craft a bypass. More specifically, they were able to append selected lists of strings to malicious files, which led to the capability to change its score in Cylance significantly and avoid detection. This method proved successful for 100% of the top 10 malware from May 2019, and close to 90% for a larger sample of 384 malware samples. Another model that was prone to prompt attacks was MATHGPT large language model. This application would create code from prompts that would then compute the answer for the user. However, this also meant that the user had the ability to directly write code in the application's backend processing. As we can see with some of the prompts listed here, the malicious users were able to induce infinite loops and crash the application or return sensitive information such as environmental variables. In subsequent versions of ChatGPT, there were more safeguards implemented to reduce these rogue operations. As we saw in the previous example, most LLM are trying to construct effective algorithms to better respond to the requests of the user. In this exploit, on the 3.5 version of GPT, users were able to bypass security guardrails that would enable the user to no longer be bound to the standard restrictions by using the phrase, "do anything now." This enabled the application change state to an elevated user and run user requests that were outside of the approved queries. While this was patched in version 4, there was another method users quickly discovered to bypass controls. Here, we can see an example of a user creating a clever game where two characters are creating a story with technical details about anything the user wants. While innocent at the surface level, the story in question is about hot wiring a vehicle, which is outside of the approved discussion topics. Notice here also how the user leverages the ability of the LLM natural propensity to problem solve by building algorithms and concatenates two approved words together to make the problematic query. This example focuses on the accessibility of ML. We tend to think of the companies that have access to building these ML systems as having deep pockets and a lot of resources. However, we were able to see earlier this year that researchers at Stanford were able to recreate a ChatGPT style ML by leveraging Llama 7B, which is an open source library built by Meta. The Llama language model is one of the smallest and low cost to run models available today, and used the model to ask GPT a human created 175 question set and got 20 responses for each. This resulted in 52,000 sample conversations and cost them about $500 for the API usage. That dataset was used for post-training, which took them 3 hours by leveraging $100 of cloud compute. This shows us that with the different techs that we have today, it is entirely feasible for more of these tools to be home-built by threat actors. Let us take a look over everything that we have discussed in this presentation. As we have seen, AI ML systems are susceptible to a wide variety of attacks, some more conventional and others far more ML specific. There is currently an arms race between attacks and mitigations, and the field is rapidly developing. There is a tangible trade-off when building in guardrails to improve robustness against attacks which come at a cost to some performance and accuracy. There are certain methods that we can take to start hardening the ML process. When a model is new and security guardrails are few, do not reveal details of the architecture and data used to create the model. We have seen ways that black box models can be reverse engineered, so this is the least effective recommendation. More effective methods are ensuring the integrity of the data and the model, strictly controlling access to the data and the model, and hardening infrastructure used in producing models. The most effective but resource intensive is to provide defense against adversarial samples through adversarial training. In a world that very commonly leverages external code, supplier security is paramount. Be sure to track vulnerabilities to components used in ML process and check the integrity and origin attestation for third-party models and data. Thank you for listening to our talk. Please send us your questions on the Source Zero Conference Discord server, where we can continue the discussion on adversarial machine learning. Thank you for your time.